Okay, so let's look at the trick that's required for part D. I'm just going to put this over top so that we can still see the original question, part D, which is up here. So what we want to do is we want to find q prime of x. So my first step is going to be the same as in all the other ones. I'm going to rewrite the problem, but with different notation. This is the derivative with respect to x of the following. So I want to take the definite integral of the square root of 4 plus t from x to x squared. And there we go. Now I've got the problem just phrased differently. So now we can't just dive in quite yet because the problem is we don't have a constant. Neither of the endpoints are constant. And here's where we're actually going to use a property 4. Remember, if you have a definite integral of some function from an endpoint a to b, you can split this up into the sum of two definite integrals using some third point as an endpoint. So I can go turn the integral from a to b into the definite integral from a to c plus the definite integral from c to b for any choice of c. So what we're going to do is apply that here, and we're going to get the derivative with respect to x of the definite integral of x to 0 so that's the first definite integral I've written down, but then I'm going to add on the definite integral from 0 to x squared of the square root of 4 plus t. So I've just broken that up into the sum of two separate area calculations. Now this point C that you choose, you have a lot of freedom here. The way the picture works, it looks as if this is going to work for any choice of C so long as C lies strictly between A and B. But actually the reality is it turns out you don't even need C to be strictly between A and B. You can have C equal to A itself or B, or it could even go outside of the bounds of A and B, as long as you don't go outside of the domain of continuity for this function in here. So that's why we don't have to worry. So because 0 is certainly not outside the domain of continuity for this function. Okay, now let's look at how to tackle these individually. Well, first, I can break this up into the sum of two derivatives. So I can take this, the derivative of x to 0, the derivative of the definite integral from x to 0 of 4 plus t, plus the derivative of the integral from 0 to x squared of the square root of 4 plus t. All right, so now we can evaluate each one of these separately. Now the first one, this has got a bit of an obstacle, but it's the same as the problem we just dealt with, right? The lower bound and the upper bound are, the bottom one is the one that's non-constant and the upper bound is constant. Well, we can tackle that by just simply interchanging the order of the endpoints and multiplying by a negative after. So we can handle this one in the exact same way we did the last example. So I'll just do that step all at once. I'll pull the negative out of the derivative all in one step. There's two things happening here. First, a negative sign goes in front of the definite integral in order to change the order of the endpoints, but then that negative can come out in front, and that's what I did down here. That's where this negative comes from, and the two endpoints traded places. Now, the second one here, the lower endpoint is constant, right? That's no problem. The lower endpoint is supposed to be constant, but the upper endpoint looks a little different than what we're used to seeing. It's an x squared instead of just an x. So it doesn't immediately fit the form of the fundamental theorem of calculus, but that's okay too. We can still work around that as well. So let's deal with this one first. The first one, this derivative can cancel with the definite integral, and the x will fall in place of the t. So for that one, we're going to get negative, because that negative sign out there is still there. We're going to have negative the square root of 4 plus x. Now for the second one, what are we going to do with this x squared? Well, we're going to start off by doing the same thing. The derivative is going to cancel with the definite integral, and then the x squared is going to fall in place for the t. However, we have to apply the chain rule because this x squared is actually an inside function. So to differentiate the outside function, leaving the inside alone, which is the first factor of the chain rule formula, we're going to use the fundamental theorem of calculus. And that's going to give us the square root of 4 plus x squared. But then by the chain rule, we have to multiply by the derivative of the inside function, which is x squared. So we just multiply by 2x. So if I want to clean up my answer and write it a bit more normally, I just write it as negative the square root of 4 plus x plus 2x times the square root of 4 plus x squared. So that is how you can tackle that example. So those 4 examples really contain all the tricks that you're probably ever going to need for applying the fundamental theorem of calculus to take derivatives of area functions like this. So that's the first part of the fundamental theorem of calculus. In the next clip, we'll take a look at part 2.